In this video, we're going through the Stage 1 Spec Maths practice exam for Semester 2. So this exam is going to cover matrices, further trig, and the sequences and series topics. You also get this formula sheet. It's actually 4 pages. So you got the unit circle, trig identities, matrices, and then the sequences and series stuff. I put this on here just in case, but I'm hoping some of this is starting to become second nature and that you won't have to look up everything on the formula sheet. But let's make a start. So you got these two matrices here, and there's a couple ways we can approach this. So with the matrices on the calculator, we can actually just enter them straight into the calculator. So we can enter matrix A is going to be 4, 2, 6, 3. And we can also enter matrix B here. 1 minus 3, 5 minus 4. And then you can pretty much just use your matrix mode on the calculator to work out all this stuff. So if you want to go shift matrix alpha A plus shift matrix alpha B, that would give you matrix A plus B, which is 5 minus 1, 11 minus 1. Now, since it's one mark, that's all you need. If you want to do that by hand, you'd add. So 4 plus 1 is 5, etc., etc. A take 2B, similar thing. So shift matrix alpha A, take 2 times shift matrix alpha B, and that should give us what we want. 2, 8 minus 4, 11. Again, if you wanted to do that, you would do the 4, take away 2 lots of 1, gives you 2, and you would do the same thing for all 4 elements. A times B, we could do this properly, so 4, 2, 6, 3, times by 1 minus 3, 5 minus 4. So we got to pair up the top row with the first column. So you get 4 times 1 plus 2 times 5 is 14. Then you're going to get 4 times minus 3, 2 times minus 4. So that's minus 20. 6 and 1, 3 and 5. So that looks like 21. 6 and minus 3, 3 and minus 4. I think that's minus 30 if I'm not mistaken. But we should double check this. So again, on your calculator, shift matrix alpha A times shift matrix alpha B gives us what we want, and we should get the right answer, so that's good. Find A inverse if possible. Well, you can literally just go, I always forget how to do it on a Casio. Shift matrix alpha A inverse may work. Math error. Now I believe that's because the determinant is 0. So determinant of A is the diagonals, 4 times 3. Take 2 times 6. Which is 12 take 12, which is 0. Therefore, A inverse does not exist. Find B inverse if possible. So if I change this to be alpha B, hopefully that'll actually spit out an inverse. It does. So essentially, det B is 1 times minus 4. Take away 5 times minus 3. So this becomes minus 4 plus 15, which is 11. Therefore, B inverse is, well, you swap the, well, you go 1 over the 11, but then you swap the B bits. So 1 and minus 4 swap. And then minus 3 and 5 negate. So you're going to get 3 and minus 5. Just like that. Beautiful stuff. All right, so this would come out as minus 4 elevenths, 3 elevenths, minus 5 elevenths, 1 11th. Beautiful. Now, again, we can just double check. Yeah, that's right. Now we got to show this is a linear transformation. So in formula sheet, it does say how to show things are linear. You check TU plus V as TU plus TV, and you're going to show that K pulls out the front. So let U be U1, U2, and V is V1, V2. We can check T of U plus V is T of U1 plus V1, U2 plus V2. What does T do? It moves the bottom thing up the top. So you get U2 plus V2 up the top, and you add both elements at the bottom. Good. Now, if we look at T of U plus T of V, what we're going to get is t of u1, u2 plus t of v1, v2. So that is u2 will come up the top, and u1 plus u2 will go down the bottom. v2 will come up the top, and v1 plus v2 goes down the bottom. And if we smoosh these vectors together, we get the matching thing that we want. Yep, so these things match. Now, t of ku is going to be t of ku1, ku2, which is ku2 up the top, and it's going to be ku1 plus ku2 down the bottom. K of tu is k of t u1, u2, which is k lots of u2 up the top and u1 plus u2 down the bottom, which if you expand the k in, you get k u2 up the top and k u1 plus k u2 down the bottom. Perfect, exactly what we need. Therefore, t of u plus v is t of u plus t of v, and t of ku equals k of tu for all vectors u and v in R2 and k in R. Therefore, t is a linear transformation. Beautiful. Find T32. So T32 would move the 2 up the top, and you get 3 plus 2 down the bottom. Consider that linear transformation. We need to find S25. So essentially what we're looking at is minus 1110 times 25. So you're going to get minus 1 lots of 2 plus 1 lot of 5. So that gives you 3. And then you're going to get 1 lot of 2. So 2. All right, good. Calculate the matrix representing S and T. So we need to have our S matrix first, minus 1110 times, I might like S of T. So that times the T matrix. Now the T matrix will be just, you got to think about what it does to each one. So the top becomes just the Y bit, and the bottom becomes X plus Y, 0111. Yeah, you can sort of justify that by thinking about 0111 when it times us by X and Y would give you Y up the top and X plus Y down the bottom. So you know that works for T. All right, so this matrix, when we times them together, what do we get? Well, we get minus 1 times 0 plus 1 times 1. You're going to get minus 1 times 1 plus 1 times 1. You're going to get 1, 0, and 0, 1. And then on the bottom right, you're going to get 1. So notice that it's the identity. Comment on the geometric significance of your answer. So we could say something along the lines of, since S composed with T gives the identity matrix, this would imply that S undoes T. Or in other words, S and T are inverse transformations. This is shown through the point 3, 2 coming to 5 under T, and then to 5 going back to 3, 2 under S. So that's like very wordy, more wordy than you would need, but that's pretty much the answer you want. Next, we've got some simultaneous equations to solve. So we want to write this as a matrix. You times that by xy, and that gives you 1, 6. Therefore, usually write this as like A, X, and B. Therefore, X equals A inverse times B. So that's going to be 2 minus 3, 1, 4 inverse times 1, 6. And that's something we can do. We could do it by hand. So essentially the determinant is going to be 8 take minus 3. You get 2, 4 and 2 will swap, 3 and the 1 will negate, 1, 6. So we could do the matrix multiplication first. So you're left with 4 1s and 3 6s, so that is 22. And then minus 1 lot of 1 and 2 6s, so that's 11, which is 22 over 11 and 11 over 11, or in other words, this is just 2, 1. Now this was the matrix x, y, so therefore x equals 2, y equals 1. And we can check this is right, because if I do 2 times 2, that's 4, take 3 does give me 1. And if I do 2 plus 4 times 1, that does give me 6, so we know we're right here. You could also give your thing as a coordinate there. So you could do it with matrices on your calculator. What you could also do is you could do polysolver or equation solver or whatever. And you could actually just enter this fully in. You could solve that. But since this is a 3-mark question, I'd want to see some working out. All right, next thing we have is we have this matrix 3 minus 1 minus 9, 3. And we are timesing that by xy to get 4 minus 8. Okay, so let's call this A. Det A is going to be 3 times 3, take minus 9 times minus 1, which is 9 take 9, which is 0. Therefore, A inverse does not exist. Therefore, no unique solution. All right, now to figure out whether we've got 0 solutions or infinity solutions, we need to figure out whether one equation is a multiple of the other. So you got 3x take y equals 4, and you've got minus 9x plus 3y equals minus 8. So you want to look if one's a multiple of the other. 3 minus 9, you want to times by minus 3 to get there. Same thing here. But times minus 3 does not work to get from 4 to minus 8. Therefore, the lines are not coincident. They are parallel. Therefore, no solutions. One thing that you could do if you really wanted to is you could rearrange both these for y, graph them, and you would get a situation that looks like that. 2 parallel lines. If you had infinity solutions, those 2 lines would be sitting on top of each other. And I can give you an example of lines with infinity solutions, like something like this. Yeah, and then you could like double everything, 4x plus 6y equals 8. This would have infinity solutions, because you can see the bottom one is just 2 lots of the top one. But if I should change that to a 9, that would give me no solutions, for example. So just got to be careful there. All right. Next we got describe the geometric effect of the transformation represented by that matrix. So to figure out what type of matrix it is, you can look at all your different types of transformations. You got rotations, reflections, and dilations. Now, the negatives may clue you in. If that top left is negative and nothing else is, well, it's not going to be a rotation, because that would be negative up there and not negative down there. Is it a reflection? Well, it could be, because the top left and bottom right are negatives of each other. So yeah, it looks like a reflection, because the dilation would have zeros up there. So we reckon it might be a reflection. So essentially what you've got to do is reflection matrices tend to look like this. They look like 1 take m squared over 1 plus m squared. They look like 2m over 1 plus m squared. They look like 2m over 1 plus m squared down here, and they look like minus 1 take m squared over 1 plus m squared. So my hunch would be, because this is 5 down the bottom, 1 plus m squared equals 5. Therefore, m equals either plus or minus 2 would have to be the case. And then if you look at the top there, 1 take m squared would give you minus 3. Because you get 1 take 4. And if we look at 2m here, 2m should be 2 times 2, which is 4. So it looks like the m is positive 2. So what we have here is, if we have m is plus 2, what we have is a reflection over the line y equals 2x, because m is the slope. All right, consider that point, find the new point. So this is a really good point about exam questions in general, I tend to write the exams, and SACE will write them like this too, so that even if you couldn't get part A, you can still do part B and beyond, because you'll notice we don't actually need to know what type of transformation this is to do the next bit. Similarly, when we did the other question with this proof here, we didn't need to do that proof to do part B. It should always work like that. So you've got the 0.11, and then we want to work out what this is. Minus 3/5 of 1 plus 4/5 of 1, it gives me 1/5. And 4/5, 3/5 gives me 8/5. So that should be the new point. So that would be 0.2 and 1.6, something like that. All right. One thing that I really want to point out, and this will probably be a Desmos thing. So realistically, we're looking at the line y equals 2x. You got the 0.1, and you've also got the 0.2, 1.6. And you'll notice what happens with that blue and green point is that the blue and green point are sort of mirrored across from each other along that line there. So it does sort of look like that's right. Is that definitely right? Now, the way we can just double check, and I will need the calculator version to get the inverse matrix anyway. So we'll go into matrix mode, matrix vector. All right, so A will be a 2 by 2. It is going to be minus 3/5, 4/5, 4/5, 3/5. Exit that out. We're going to go matrix B. Should be a 1 by 2. What? Let's try that again. Dim 1 by 2. No, I always get that the wrong way around. It should be a 2 by 1, shouldn't it? Cool. And then that is just 1, 1. So in theory, if I go back into math mode and I go shift matrix A times shift matrix B, I should get that. Which, yeah, that was wrong. 8/5. Oh, 4 and 3 gives you 7, not 8. That's the issue. Because when I saw it on Desmos, I thought it looks like almost like the reflection, but a little bit off. That should be a bit better. Now that blue and green line like the reflected versions across that red line there. All right, so that's good. Find the matrix which represents T inverse. Now you could work it out by hand, but I'm kind of sick of doing those now, so we can just use the calculator. T inverse is the matrix A inverse, which is that minus 0.6, 0.8, 0.8, 0.6. Now you might notice this is exactly the same as T. Minus 3/5, 4/5, 4/5, 3/5. Yeah, it literally is the same as T. Now, why is that? Well, because imagine taking this blue point and reflecting it over to the green point. Now, if you wanted to undo that, well, you would just do the same thing. You would reflect the green point back to the blue point. So reflections are self-inverse. That's always what you need to know. If you have a reflection and you want the inverse, you just do the reflection again. So as T inverse equals T, the transformation is its own inverse. To undo a reflection over the line y equals 2x, we can just do another reflection over the line y equals 2x. Done. All right, so next, solve these trig equations. Cos theta equals 0. Now this is where a unit circle is really going to come in handy. Where are all the points where cos is 0? Where it's where the x coordinate is 0. It's going to be at pi over 2 and 3 pi over 2. All right. Theta equals pi over 2, 3 pi over 2. Where is 2 sine of theta equal 1? Well, that's going to be sine of theta equals a half. Therefore, theta equals, now, let's look where all the sines are a half. That's going to be at pi over 6 and again at 5 pi over 6. Yeah, that's not all the answers because we're going up to 3 pi. So what we need to do is we need to add on 2 pi from our previous answers. which will be the same as adding on 12 pi over 6. So that's going to give us 13 pi over 6 there. And if we try the next one, 5 plus another 12 will give us 17 pi over 6, which I actually think is still in your range. That's good. And then if we want the next step forward, 13 plus 12 will be 25 pi over 6. But this thing is too big. You could also get negatives, but that wouldn't work either. So you actually get 4 answers here. Theta is pi over 6, 5 pi over 6, 13 pi over 6, and 17 pi over 6, because you wouldn't want to blow past 18 pi over 6, which is 3 pi. Next, we got this one. So tan of theta plus pi over 8 equals minus 1, because if you move the 3 over there, you get that. So we got to think about all the bits where tan is minus 1. That happens at 3 pi over 4 and 7 pi over 4. So you're going to get theta plus pi over 8 equals 3 pi over 4 or 7 pi over 4. So therefore, theta equals, 3 pi over 4 take pi over 8, or 7 pi over 4 take pi over 8, which is going to give you 5 pi over 8, or 13 pi over 8. Now, a good strategy for adding these weird numbers is you can just do 3/4, take an eighth on your calculator, and that will spit out what you need, like it's 5 pi over 8, for example. Now, we haven't got all the solutions because I believe there's also another one that's negative. Now, this thing here, too big. But we also have 5 pi over 8 take, 13 pi over 8 take 2 pi, which is 13 pi over 8 take 16 pi over 8, which is minus 3 pi over 8. Now, how do you double check this? So your answers are theta equals 5 pi over 8 and minus 3 pi over 8. Let's double check this, because you can cheat these questions by just graphing it. It will take you a little while, but it's definitely worth doing if you have the extra time. So we'll delete out all those old functions that we got there. Some beautiful functions. Shame to get rid of them. And we're going to go tan of x plus pi over 8 plus 3, and then on the other line I'll just graph 2, and you'll be able to see really clearly how many intersections there are. We'll just go from minus pi up to pi, and we'll just graph that. Yeah, so you can sort of see there are 2 spots where it works, and if we go for the intersection of those 2 spots, you can see one of them's at minus 1.178, which is a very fancy way of saying minus 3 pi over 8. And the other one is at 1.963, which is a fancy way of saying 5 pi over 8. Now you can actually just double check that, because if you go minus 3 pi over 8, I believe that was the number we got before, and 5 pi over 8 is also that other number we got before, 1.963, which should match those 1.178, 1.963, should match those intersection points. You could also do xcal, yeah, up to you. Next one we got is this one. We need to use a trig identity first to simplify it. Cos squared takes sine squared, there it is cos of 2 theta. So we'll do that. So cos squared theta takes sine squared theta equals 1 over root 2. Therefore, cos of 2 theta equals 1 over root 2. So we need to look for where the cos is 1 over root 2. Back on our unit circle. This is the same as root 2 over 2. So this happens at pi over 4 and 7 pi over 4. 2 theta is pi over 4, or 7 pi over 4. Therefore, theta is pi over 8, or 7 pi over 8. Those are your only two solutions. If you want to make sure you can do that graphing thing again and double check, you should only have those two intersection points. All right, beautiful stuff. Wonderful. All right. All right, pendulum swings left and right like that. So what we've got to do is graph this. Now, graphing questions are usually a very easy way to get a lot of marks. In my experience doing the year 12 exams, they tend to give you a grid already, like they don't expect you to draw a grid, so that's always good news because you can just know what your window is pretty much immediately. Like X seems to go from 0 to 16 and Y looks like it's minus 40 to 40-ish. 30 times 1.2 to the power of minus X. Also make sure in radians when you do this, it's very easy to accidentally forget that. Pi over 2 times bracket X take 0.074. Yep. So let's set up our windows. V window X min can be 0 and we'll go up to 16. Y min can be, let's go minus 40 to 40. And we'll draw that. Beautiful, beautiful, beautiful. Now, this is a pendulum that's swinging. And hopefully it makes sense that as the pendulum is swinging, it's going to be like losing energy and losing speed and stuff. So it will gradually start slowing down and get less and less swingy. So let's trace 0 and see what that is. The height starts at 29.797, very nearly 30. And I'm actually going to mark that 0, 29.797, because we'll see this will come in handy later. Then we might as well start just finding our minimums and stuff. So we got essentially 2 and minus 20.692. Then our next one, we'll just do a lot of our minimums first. So the next minimum is at 6 minus 9.979. Next minimum is at 10 minus 4.812. And next minimum is at 14 and minus 2.321. All right, and then we're going to have our maximums. So Shift G solve max 4, 14.369. Next max across 8, 6.929. $12, 3.341. Last one's, well, it won't show it on this window, but it's at 16. So we'll just, I might actually bump up the window just the tiniest little bit. 16.1. Get that last maximum. 16, 1.612. All right, so now once a graph from 0 to 16, so we can sort of draw this graph in like so. Come down and go through there. Go up, down. Beautiful. You can draw an arrow to keep going. You can also label it S of t. equals 30 times 1.2 to the minus t cos of pi over 2 t take 0.074. So you label it with the equation, that's done. Find the approximate time. Now the reason I filled in all these maximum is just that the t is 2 and the s is minus 20.692 centimeters. Cool. So displacement, so 20.692 centimeters left. Because left is down, right is up. That's what you got to remember for this graph. All right. Now, this table shows those maximums. So 4, 14.37, we've got essentially 6 minus 9.98. So you can use this to double check that you've sort of graphed everything right. And you basically just got to fill in the missing one. So this was 2 and 20.69. The next one was 10 minus 4.82. And the last one was at 12, 3.341. Beautiful. The values form a series, determine whether or not it's arithmetic or geometric. This is geometric. Now, what are we timesing by each time to get it? That's the question. It's really easy to check this actually, because what you can do is you can just divide the term by the term before it. So if I take 20.69 and I divide it by 29.80, it's 0.694. So we're timesing by 0.694 to get it. I might actually do that in a different color. All right. Again, we can actually, 14.37 divided by 20.69, timesing by 0.694 again, roughly. Yeah, it's actually not positive 0.694, but it's actually negative because it's flipping each time. So timesing by negative 0.694 again, let's just double check that. Or even if I do like 14.37 times by negative 0.694, that should give you the next one. Times by negative 0.694, that should give me the next one, and etc. etc. So geometric common ratio R roughly equals 0.694. Hence find the maximum displacement on swing 20. So T1 is actually 20.69. You just got to be really careful there. So T20 is what we're looking for. So a general geometric series formula will look like this. For the nth term, it's Tn is T1 R to the n minus 1. So T20 is T1 times R to the 20 take 1, which is going to be 20.69 times 0.694, and that's a negative to the power of 19. .02, yeah, roughly 0.02 centimeters. Great, so that's really good. That sort of checks out as well, actually. So when will the swing be the first to be less than 1 centimeter either direction? So maybe what you could do is you could do some trial and error. T6 is 3.341, and we could start with that. Times minus 0.694. Oh, the other thing you could do to double check this T20 answer is you'll notice all the that should be negative. T1 is actually negative that, so that should be positive. My bad, positive 0.02. You'll notice that all the even numbers are negative and all the odd terms are positive. All the even swings are positive and all the odd swings are negative. So this is an even swing, so it should be positive as well. T6 is that. T7 is going to be 3.341 times that, which is minus 2.318. T8 roughly equals times minus 0.694, 1.609. T9 roughly equals times 0. Times minus 694 minus 1.117 times minus 0.694, 0.775. So the 10th swing. Explain why the total distance is that. So you've really got to look at your swings. So it's going to be the 29.797. 29.797 plus all the way down to 20.692 plus another 20.692 coming back up. Then you've got plus 14.369, which is up. Just covered after 6 seconds. What do we hit? 6, yep. Plus 14.369, which is down. Plus that next height, which goes down to 9.979, which is going further down. All right, so let's add up all these numbers. 29.797 plus 2 times 20.692 plus 2 lots of 14.369 plus 9.979, 109.898, roughly. I might actually just get rid of that decimal. The reason it's not perfect is because rounding, but roughly equals 109 centimeters. Good. Maybe like roughly 110. Find the total distance covered. So basically, distance is going to be the T0 plus 2 lots of T1 plus 2 lots of T2 plus 2 lots of T3 plus all the way up to infinity. So the reason you only get 1 lot of T0 is it's just coming down. It's not going like up then down there. All right, so this is 29.797 plus 2 times the sum of k equals 1 to infinity of tk. Now the way we work out that is the ratio thing, 29.797 plus the ratio t1, r to the n take 1 over r take 1. Actually, no, the infinite version doesn't have that bit in it. It's just t1 over, let me make sure I get this right. T1 over 1 take r, I think, is the infinite. Yep, t1 over 1 take r. T1 over 1 take r. Which is 29.797 plus, what is T1? T1 is, now you got to be careful with the negatives. So you've just got to interpret these as all positives now. So 20.69 over 1 take, oh no, this is still 2 lots of that series as well. 1 take the ratio, which is 0.694, roughly equal to, so let's work that out, 29.77 plus 2 times 20.69 over brackets 1 take 0.694, 165.025. All right. Now, time for an actual check here. So 9.979 is the last one we added, and we're already up to 110. After 9, it's going to dip down to like 6 and then 4 and then 3. So if I've got like 110 plus the other 9.98 that we didn't add on before, plus 2 times 6.93 plus 2 times 4.82 plus 2 times 3. 41. We're already at 150 and those distances are shrinking very quickly. So 165 is actually a realistic link there. You'd also be fancy and add on like all these other ones. So like, you know, plus 2 times 2.318 plus 2 times 1.609 plus 2 times 1.117 plus 2 times 0.775, etc. You're getting already up to 161. So you can see that, like, because these swings are getting so small, you're not adding much more distance on after a while, and you're going to sort of end up at 165. We're already almost there after we've got the whole 10 swings. All right. Consider that sequence. Decide whether it's arithmetic or geometric. This is arithmetic. Common difference, D is -4. The first term is T1 equals 3. Find T33. So there's a general formula for what term is. Tn is T1, n take 1D. So T33 is 3 plus 33 take 1 times -4, which is 3 plus 32 times -4. Let's see what that is. -125. Now, you can be really cheeky with this, and you can go like 3 and then just like take 4 a bunch of times. You know, you could keep doing that 33 times, and you'd actually get down to -125. Find the first term, which is smaller than -50. So this is sort of like a, you'd want to solve for Tn equals -50. Therefore, -50 would be 3 lots of n take 1 times -4. Therefore, -53, that's 3 plus, -53 equals n take 1 times -4. Therefore, n take 1 is -53 over -4. Therefore, n take 1 roughly equals 13.25. Therefore, n roughly equals 14.25. The 15th term will be under -50. All right, because you'd have to round up to 15. The 14th term won't quite cut it, but the 15th term will. Let's double check this. So 3 plus 14 take 1 times -4 gives you -49. 3 plus 15 take 1 times by -4 does give you that 53. Find S20. So there's a general formula for sum of an arithmetic sequence. It's that n over 2. Sn is n over 2 T1 plus n take 1 D. So this is S20 is 20 over 2. 3 plus 20 take 1 times by -4. This is 10, 3 plus 19 times by -4. 10, 3 plus 19 times -4. -730. Yeah, which sort of makes sense because those numbers are getting big. Yeah. All right, cool. Validate these sums. A k equals 1. This is 3. A k equals 2. This is 3. A k equals 3. This is 3. A k equals 4. This is 3. And a k equals 5. This is 3. The whole thing's 15. Now, I want you to make sure that you're doing the sums on your calculator as well, and just double checking. So this is 3, and we're looking at x equals 1 all the way up to 5. Done. All right, next we've got this. So T1 is 2, R is 3. This is a geometric series, so we're going to use Sn is T1 R to the n take 1 over R take 1. That's geometric series formula. It's on your formula sheet. That's 2, 3 to the, so S5 is what we're looking at. 3 to the 5 take 1 over 3 take 1, which is 2 lots of, actually let's just work that out. 2 lots of 3 to the 5 take 1 over 3 take 1, 242. Now let's actually work this out using the sum mode on the calculator. So 2 times 3 to the power of x take 1. And x goes from 1 all the way up to 5. 242. Next one. Similar, very similar, but it's arithmetic. T1 is 2, D is 3. And we're adding up to 20. There's a formula for this. So Sn is n over 2, 2t1 plus n take 1 d. So that's going to be 20 over 2, 2 times 2, plus 3, 20 take 1. Okay, good. So let's work that out. Don Cassius. Better, 610. Now, again, let's just double check that. So 2 plus 3 brackets x take 1. I've got one too many brackets there, don't I? Yep. X is 1 all the way up to 20. 610. 1/5 to the power of k. K equals 1 to infinity. So S infinity is T1 over 1 take R. T1's actually a fifth over 1 take a fifth, which is 1/5 over 4/5, which is a quarter. Yeah. So let's just try that. So what we're looking at is another sum. You got a fifth to the power of x, and x is 1 all the way up to a big, yeah, it's about a quarter. Yeah, the calculator says a quarter, but it's actually slightly less that is. All right, good. Now we get a matrix form. A cubed, unsurprisingly, is that, and then that, but we will work it out properly. So on your calculator, you just want to enter the matrix mode. Matrix vector. All right, so enter A, 2 by 2 is 2002. Exit. Shift matrix alpha A to the power of 2 is the thing that the question said. Change that to a 3. It's the thing that I said before, and if we change it to a 4, it's also that thing. Make a conjecture. AN equals 2 to the n, O, 2 to the n. It's actually quite clear, because if A is just 2 lots of the identity matrix, then like A to the n is 2i to the n, which is 2 to the n times I to the n, which is 2 to the n I. So we won't actually need induction to prove this, but, well, we might as well do it. It's a nice, straightforward matrix induction question. So, yeah, like 2 to the n times I would be the conjecture we're making anyway. So prove your conjecture using induction. So P1, okay, we'll be very clear. Let Pn, for all, let Pn be the statement A to the n equals 2 to the n, O, 2 to the n. P1, left-hand side, we've got A to the 1, which is 2,002 to the 1, which is 2002. On the right-hand side, what do we got? We got 2 to the 1, 002 to the 1, which is 2002. Brilliant. P1's true. P1 true. Assume PK is true. Therefore, A to the K is 2 to the K, 002 to the K. PK plus 1, we need to look at our want to show, or in other words, our right-hand side. This would look like 2 to the K plus 1, 002 to the K plus 1. So a to the k plus 1 is on our left-hand side. We'll split this up into a to the k times by a. Call this star. So using star, this is 2 to the k 2 to the k times by 2002 using star, which is 2 to the k times 2 plus o, o plus o, o plus o, and o plus 2 to the k times 2. And using your index laws, add the powers, so you get 2 to the k plus 1, o, 2 to the k plus 1, 2 to the k plus 1. Index laws, 2 to the 1 times 2 to the k is 2 to the 1 plus k. Therefore, pk plus 1 is true. Therefore, by induction, a to the n is 2 to the n 2 to the n for all n in z. Beautiful. All right, next we got this question about rectangles, which is very fun. Y equals root of 1 take x squared. And if you're, now I didn't say this in the question, but if you basically what this equation is a rearrangement of this one, x squared plus y squared equals 1. And you might remember that from methods as a circle, center 0, and radius 1. And that's, if you rearrange that equation for y, you get to that thing. All right, explain why the height of the leftmost rectangle in the two rectangle estimate is 0.75. So y is this height, 0.75. Height will equal f of 0.5. Yeah, so maybe what we could do is we could say like let f of x equal root 1 take x squared. Cool. I might actually rewrite that question, use f of x instead of y when you see it. But basically it's root of 1 take 0.5 squared, which is root of 1 take 0.25, which is root of 0.75. Hence calculate the value. So area is going to be all the rectangles added together and the length times width. So it's going to be the width, the width is 0.5 times root 0.75 for the first rectangle, plus 0.5 times the other height is 0. And you can actually work that out because it's square root of 1 take 1 squared, which is 0, which is 0.5 root 75. Root 3 over 4 if you want, but probably S to D is 0.433 square units. So the 4 rectangle estimate is that, so area is going to be, each of these rectangles are 0.25 wide because you're splitting up the 1 into 4 parts. So 0.25 times root 1 take 0.25 squared plus 0.25 root 1 take 0.5 squared plus 0.25 times root 1 take 0.75 squared plus 0 on the end, which roughly equals 2. It would be really lazy here. You could actually use the sum mode on your calculator and work out how to do it as a sum. 1 take 0.5 squared plus 0.25 square root of 1 take 0.75 squared. 0.623. 0.62392 roughly equals 0.624 units squared. Usually giving a few more decimal places than the answer, then rounding it back would show the marker that like you've actually worked out the number and you're not just saying that it's equal to 0.624. So here you can see we've used 50 rectangles, and what do you think would happen to the area? Well, in those areas here, you've got heaps of gaps that you're not accounting for. But in this area, there's like less gaps. So the 50 rectangle estimate leaves less gaps of unaccounted area. So this means our estimate should be closer to the real area. Using more rectangles will give a better estimate. Explain why the estimate can be found using the sum there. So this here is the width of each rectangle, like it was 0.25 for the last question. This here is the height of each rectangle, and then this bit is add all rectangles. Area is the sum of the areas, the sum of the length times width, essentially. So that's like the formal version of what we were doing in that earlier part. Here we only had 4 rectangles. You'll notice the last bit there will always be 0. All right, so now we're going to calculate some sums. So math, cross sum. Okay, so 1/10 times root 1 take x over 10 squared. X goes from 1 up to 10. 0.726. Now what we got to do is take our previous thing. We got to change all of our 10s to 50s. Change that one, and don't forget to change the actual ones in the sum. So that will change to a 50. That will change to a 50. 0.774 or 0.775. All right. Next we got this one. We got to change all of our things to 100. .780. All right, so it looks like that area is approaching the actual value, which is in the high 0.7s or something like that. You can see the first estimate's really bad, and then as we're getting more and more, then we're actually getting to the true area. Now, based on your answer from D, these values should approach the true area under the graph. For example, if we use 10,000 rather than 100, we get 0.785. Multiply this number by 4 and comment on the geometric significance. So 0.785 times by 4, you will absolutely love this. It's a very special number. It's 3.14, which you may recognize as pi. Wow. All right, so what's going on here? First of all, let's just calculate pi and just double check. Yes, no, yes, that is about 3.14. So basically what's going on is the area under curve equals a quarter of the circle. All right, full circle area is pi r squared, but this is pi times 1 squared, which is pi. Therefore, area under curve times by 4 equals pi, since the area under curve is the quarter circle. Yeah, it's basically what we're saying. It's like, if you take this entire circle and like step it all out, the whole area under that is pi, because we got pi r squared, and that radius is 1. So this quarter area that we're working out should be pi over 4 if you wanted to work out the exact area. And it turns out that if you work out pi over 4, it is that number that's about 0.785, which is what our areas were approaching. So the cool thing is, if you ever want to work out pi and you can't remember where the button is on your calculator, just do this sum and put a number much bigger than 100 in there, like 10,000, and then multiply your answer by 4, and there you've got pi. Much, much easier. And that's the end of the exam.